Gravity and Simple Harmonic Motion Review 6. An asteroid is in elliptical orbit around a star with perihelion and aphelion locations as shown. Assume that the asteroid's mass remains constant. Use conservation of angular momentum to find the speed at aphelion. So that's down here. We're looking for the speed. We know the speed at perihelion, which is 28,000 meters per second, and we want to know what the speed is down there. Now, the reason we can use conservation of angular momentum is because there's no net torque on the asteroid. So the initial angular momentum must equal the final angular momentum. One equation for angular momentum was the mass times the velocity times r perpendicular. R perpendicular being perpendicular to the velocity is that RA value for aphelion and that R value for perihelion. The mass is the same. We're assuming the mass stays constant. That's what it says in the problem. And so it looks to me like 3 of these 4 variables are given. And so VA is going to be VP RP divided by RA. The velocity at perihelion is 28,000. R perpendicular at perihelion is 1 times 10 to the 10th meters. I'm leaving the units off because I checked them. Meters, meters per second, kilograms, everything that's given is good. R perpendicular at aphelion is 4 times 10 to the 10th. The 10 to the 10ths cancel. That's 28,000 divided by 4. That's 7,000. 7,000 meters per second, which makes sense, at least in the sense that the further away something is, the slower it's going to be going. So that seems to make sense. All right, assuming the star's mass is given as that, use conservation of energy to determine the velocity at aphelion. So we're going to have kinetic energy at aphelion plus gravitational potential energy, which is a negative quantity. So that's going to be G times, I'll call it big M, that'll be the mass of the star, times the mass of the satellite, divided by the distance between them, which is RA. That's the total energy, kinetic plus gravitational potential, when we're at aphelion. When we're at perihelion, it's a similar looking expression. The mass of the asteroid is the same in all of these. And so if we, how can we simplify this? How about we double everything? Can we do that? Multiply everything by 2. So that 1/2 goes away. We end up with a 2 in front of that G. That 1/2 goes away. We end up with a 2 in front of that. Let's solve this for VA. Can we do that? VA, we're going to have to move that over there. So we're going to get VP squared over there. And then we're going to put that over there. So we're going to get 2GM 1 over RA minus 1 over RP. Close parentheses. Add those up. Make the square root. All right, I went through that a little bit quickly, but you check and make sure that we're good there. Let's see what this would be, just for fun. We usually don't type in things on these videos. I usually do it ahead of time, but you know what? I'm just curious how this is actually going to work out. Let's see if this expression works. All right, VP is 28,000. We got to square that, plus 2. G is 6.67 times 10 to the negative 11th. The mass of this star, we're told, is 7.346 times 10 to the 28th. And then this fraction is going to be 1 over RA is 4 times 10 to the 10th minus 1 over 1 times 10 to the 10th. And then we have to take the square root of that. I'm going to type that in, and let's see what we get here, just for fun. All right, I'm going to start over here. We're going to go 4 times 10 to the 10th, 1 over that, minus 1 times 10 to the 10th, 1 over that, equals that thing, times 7.346 EE 28, times 6.67 EE negative 11, times 2 equals plus 28,000 squared equals, take the square root equals. Oh! 7,000, look at that. Oh, man. As Sheldon would say, it's a Saturnalia miracle. Look at that. Pretty neat. All right, one quick question and then we're done with this video. Which graph depicts how absolute gravitational potential energy varies with separation between two masses? Absolute gravitational potential energy is always negative. Can't be those. And it's proportional to 1 over r. So as r gets bigger, the magnitude gets tinier and tinier and tinier. Right there.